Great. And okay, so welcome to lecture 4. So today we're going to talk about we're going to compare different types of randomness of the verifier, specifically public coins versus private coins. So we've already discussed how randomness is essential for interactive proofs, but we've also seen how it comes in different forms. For example, we have seen a two-message interactive proof for graph non-isomorphism. And there, the main point of soundness, it relies on the fact that the verifier's random bit remains a secret during the interaction, okay? Because the prover is kind of trying to guess it, and depending upon whether the graphs are isomorphic or not, if they're not isomorphic, he can figure it out, and if they are isomorphic, he can't. Yet, we have also seen sum check style interactive proofs. For example, the one for TQBF, those tend to be sort of more rounds rather than just two messages. And there, all the verifier randomness is sent to the prover. Or rather, it is anytime the verifier samples some randomness, it is sent right away. It doesn't mean that it first samples all the randomness and sends all the randomness right away. It's that anytime the verifier needs to sample randomness, it's sent right away. At any moment in time, there is no secret randomness around. Okay? So today we're going to try to understand how these settings compare. And in more detail, we're going to say that a verifier V is public coin if its every message is just a freshly sampled uniform random string of some prescribed length. Okay? Otherwise, we say that the verifier is private coin. Of course, in the sum check protocol, the randomness that was sent in every round was always the same length, but it's okay. Maybe in some other protocol, in one round you send one field element, in the next round two random field elements. The important thing is that for it to be public coin, every time the verifier opens its mouth, out comes a freshly sampled random string of some sort. Notice that whenever you have such a verifier, all kind of interesting verifier logic can just be pushed until after the interaction. So even though we described, for example, Shamir's protocol with certain tests done in certain rounds, that was just for the convenience of exposition. There was nothing really that the verifier had to do at that point. It was just sampling randomness and sending it, so you can just postpone all of those tests till after the interaction, right? So during interaction, the verifier is just there to provide randomness at the right points. Now, from a complexity perspective, we have, when you want to emphasize that an interactive proof is public coin, there is different notation that we use. Those are the complexity classes AM and MA. These are languages decidable via public coin, K-round interactive proofs where either the verifier or prover moves first respectively. This notation of AM and MA is historical, comes from the use of the terminology of Arthur Merlin proofs, where Arthur denotes the sort of mortal verifier and Merlin denotes the wizard, sort of all-powerful prover. And AM denotes that the verifier moves first during the interaction, so A first and then M, so Arthur first and then Merlin, and then they kind of continue like that for whatever number of rounds. And MA denotes that Merlin starts first, the prover starts first. Okay? Arthur Merlin proofs are public coin interactive proofs. I will not be using much the Arthur Merlin terminology, just that for denoting complexity classes, that is what we have today. So it is pretty clear that if you give me some round complexity function k, AM or MAK, they are just subsets of IPK. Okay, and also in IP we didn't really specify, we weren't really interested in who starts first. So why? Because interactive proofs can be either public coin or private coin. In particular, they can be public coin. So we know that public coin interactive proofs are no more powerful than general interactive proofs. Yet, you may ask, are general interactive proofs more powerful? Notice that they shouldn't be, right? We already know that, right? We proved that all of P-space has a public coin interactive proof, right? And that was, we also proved that interactive proofs can only talk about p-space, so we know they're not more powerful. So one question we could ask is, maybe they help us with round complexity, because look, in example 1, we have a 2-message interactive proof for GNI, but then if we want to try to construct a public coin interactive proof for GNI, maybe we're going to start using the sum check protocol, and maybe we might get large round complexity. Turns out that's actually not the case. There is a rather surprising result that there is a way to transform any interactive proof, in particular a private coin interactive proof, into a corresponding public coin interactive proof at the cost of only one extra round. Okay? So this is a rather involved result, so we'll not prove it in class. Instead, we'll prove a special case from it that is, I think, very cute and very nice to look at. Before I move on, are there any questions? Okay, so what we will do today is we're going to revisit the special case of graph non-isomorphism, and we will prove that we can actually exhibit a 1-round or 2-message public coin interactive proof for graph non-isomorphism. Okay, this should kind of be like an intriguing result, right? It's kind of totally not clear how we're going to do that. At a very high level, the main idea behind designing a public coin interactive proof for graph isomorphism, and more generally any other language, is we're going to look at it in a more quantitative way, and specifically we're going to define this set S. Okay, so you give me two graphs, G0 and G1, maybe they're isomorphic, maybe they're not, and this set S is going to be all graphs that are isomorphic to either G0 or G1. Okay? Now, notice that if I have a graph that I claim is in this set S, and I'm the prover, I can convince you of that because I just give you H, right? The graph H allegedly in the set. And for if H really is in the set, that it means it is isomorphic to either G0 or G1, and I can just give you an isomorphism that shows that, so I can convince you that a element is indeed in the set. Okay, so this kind of set is in NP. Moreover, if the two graphs are isomorphic, you expect this set to be just, all permutations. Okay, I'm kind of making some assumptions here. I'll come back to that in a moment. But intuitively, there is just one equivalence class because G0 is isomorphic to G1, H is isomorphic to either G0 or G1, but anyways isomorphic to one another. So there is only one equivalence class. Yet if they're not isomorphic, this set doubles in size. There are two disjoint equivalence classes. So depending upon whether G0 or G1 are isomorphic, this set changes in size. Now this is not entirely accurate because it really depends on whether the so-called automorphism group of the two graphs is the identity or not. Okay, what is the automorphism group? These are isomorphisms from the graph to itself. Okay, so if kind of the automorphism group is degenerate, is just the identity, then really there are in principle n factorial isomorphic graphs to G0 or G1. And throughout we're just going to assume that's the case. Just to let you know, you can remove this assumption easily by considering a related set that I wrote here in gray. This set S consider a pair which is an isomorphic graph H and then an isomorphism psi which is in the automorphism group of H. Okay? When you consider this set, it kind of while before you were kind of modding out by the automorphism, here you kind of the automorphism group here, you kind of bring it back in. And again, this set has size either n factorial or 2n factorial. We'll just primarily kind of shove this under the carpet and just, you can think about it, we're assuming that G0 and G1 are special and that they have a degenerate automorphism group. The main point I want you to take away from this is that depending upon whether G0 and G1 are isomorphic or not, there is a set that has one size or twice that size. That is the sense in which we're looking at graph isomorphism in a more quantitative way. So this simple observation is actually going to take us very far Because now, look, it really suffices for the prover to convince that this set has size 2n factorial 2 times parenthesis n factorial rather than size n factorial. That's all we really need to do. We need a public coin interactive proof for this task. That will suffice for our purposes. So the way this is done is we're gonna rely on a favorite tool of theoretical computer scientists, that is pairwise independent hashing. I'm gonna remind you of what it is. Then from it, we're gonna design a public coin, so-called set lower bound protocol. We'll explain what it means in a moment. And then we're gonna use the set lower bound protocol to design a public coin interactive proof for graph isomorphism by using this perspective of the set S. Okay, so that is the plan. Any questions so far? Okay, cool. Note that curiously, this approach doesn't actually take an arithmetization route. It's kind of, to some extent, quite combinatorial. Okay, so what I'm going to do is I'm going to just have a quick slide on just reminding you what is pairwise independent hashing. So first, a family of functions, HM, well, I don't know why it should say, why it's HMN, it should say HML, okay, and that's of functions. So these are functions that map M bits to L bits, okay? We say that it is pairwise independent if anytime you take two distinct inputs, x and x prime, and two outputs, y and y prime, possibly the same, possibly not, doesn't matter. And you look at the probability that if you sample a random hash function from this family, and you ask, do I have both x going to y and x prime going to y prime, okay? Now, if this function was completely random, because you are mapping two distinct inputs, the probability that h of x is y would be 1 over 2 to the L, and also h of x prime, again, x is different x prime, equals some other y prime, is also 1 over 2 to the L. And these are independent events, so you would get 1 over 2 to the 2 times L. Pairwise independent says that this property of a random function is all you're going to require. Okay, so the only thing that this hash function is fulfill is this one property of random functions. What happens if you take x, x prime, and x double prime? Will you get 1 over 2 to the 3L? Maybe, maybe not. It doesn't matter. Okay, we will not rely on that. Okay, in fact, generally the constructions we will consider will not satisfy that property. So the only thing we're going to use is this kind of a pairwise independence property. Okay, these two events behave as if they were independent. So that is a pairwise independent function. The canonical example that you may have seen in other courses, even undergrad courses, of a pairwise independent hash function is a random affine function. So for example, you can consider the field, the binary field f 2 to the m, so the binary field of size 2 to the m, and you just set the function family to be all functions of the form ax plus b, where a and b are two elements in the field. Okay? Let's quickly see why this is a pairwise independent. We want to look at whether a random function from the family that is equivalent to sampling a and b independently. So we sample a and b, these are elements in the field. And we look at the event whether h of ab of x equals y and h of ab of x prime equals y prime. So by construction, that we're comparing these two events, ax plus b equals y and ax prime plus b equals y prime. Because x and x prime are different, we can kind of solve the system of linear equations, and we have the two equations a equals y minus y prime over x minus x prime, and b equals y minus x. Now let's see what's happening. This is just a fixed value. This is just something, some element in the field. And we're asking, what is the probability that if I sample A and B independently as two random field elements, A happens to equals this one? Well, that is 1 over 2 to the m, right? This is just a random element that's a fixed element. Now, for any choice of A, this is also just some element. And what is the probability that B equals that thing? Again, some independent 1 over 2 to the m probability. So these two things multiply and we get 1 over 2 to the 2m. Okay? So, and notice how the fact that we have two terms here, A and B, that is exactly what it creates the independence here and how we get this desired probability. Notice that this was just a special case where I set the output size to equal the input size. We're actually interested in a setting. We will be using a setting where we're compressing. So we want the output size to be smaller than the input size. So what do? We just modify this affine function in some natural way. We're going to basically take the same thing, but we're just going to truncate the output. Okay, so we're going to parse this field element as some integer, again, some canonical way. And we're going to truncate it from m bits to L bits. Okay, for example, you take the lowest order L bits. Okay, so that's a pretty crude way of sort of making the function compressing. Now, we did change the function, so what happened to the pairwise independent property, we should check that again, that it holds. It does, so you can convince yourself, very roughly speaking, there are 2 to the m minus L choices of A that satisfy this first property, okay? So again, we have y minus y prime, that's some fixed element that's a fixed L-bit integer, right? And we have x minus x prime, we multiplied by A and we mod out by 2 to the L. Now A has size 2 to the m, right? And we multiply by some fixed element, that's gonna get again some element that consists of m bits. And it's pretty easy to convince yourself that there is actually 2 to the m minus L choices of A that all of them map to this very same y minus y prime integer. Okay, that is L-bit integer. And for any such choice of A, there are 2 to the m minus L choices of B such that ax plus b mod 2 to the L is y. Okay, I'm just doing precisely a very similar argument as this one, except that instead of having one choice per equation, I have 2 to the m minus L choices per equation, the top one and the bottom one. Okay, now that gives us 2 to the m minus L times 2 to the m minus L divided by 2 to the m times 2 to the m, and overall that gives us 1 over 2 to the 2L. Okay? So, yeah. Are there any questions? This is a construction that, you may have seen maybe in some semesters in 170, maybe even CS70 comes up whenever you're doing things like studying dictionaries and you're constructing hash tables with things like universal hashing. Okay? There's a very similar construction that you do. And sometimes people consider the binary field, sometimes people consider prime fields. In both cases, you consider random affine functions over whatever field. This is just to remind you, we have pairwise independent hashing. And now, notice that because a random function satisfies pairwise independent hashing, it's not about finding a pairwise independent hash function, it's about finding one that is efficiently computable. And you will agree with me that random affine functions are efficiently computable, right? Because you take your input, you do one field operation, that's AX, you do plus B, that's another field addition, then you do a mod, that's a GCD algorithm. All of this is efficient now, okay? So it is efficient as opposed to like a random function. And we can do this for any choice of M and any choice of L. This is all I'm going to say about constructions and pairwise independent hashing. Are there questions? I don't hear anything. And I hope my speakers are working. So if you're speaking and I'm not answering to you, please write in chat. And okay, so this is just a tool, and we're now going to use it to construct a set lower bound protocol. So in the abstract, we have some set S, okay, of m bit elements. And this set is an MP in the sense that we can check that X is an S with the help of a prover, okay? It can just give us some short proof certifying that some X really indeed is an S. And we seek an interactive proof for also called promise problem. We want to accept with high probability if S is above some bound. For us, our bound is going to be 2 times parenthesis n factorial. And we're going to say no if this bound is smaller than or equal to, let's say, b over 2. Okay, for us, that bound is going to be n factorial. All right? We're not interested what happens in between because in our application we don't care. Okay, so that's why this is a promise problem. Okay, so let's design it. So we have the prover and we have the verifier. Both know about the set S. The verifier receives this desired bound B. And the way the program is going to go is just going to be one round, okay? First, the verifier is going to compute some output size L for a hash function. This L is going to be chosen to be satisfying this inequality. So B is at most half of 2 to the L and at least a quarter of 2 to the L. And then the verifier is going to sample 2 objects, a random hash function from HML. Again, remember, M is the input size for describing an element from the set, and L is whatever we just chose right now. It's related to the bound. And then it's going to pick a random image of the hash function. Okay, so it's a random Y, it's in the image, it's in the codomain 0, 1 to the L. And it's going to send to the prover, here is my random H and random Y. Notice that this is a public coin protocol because it's just sending, a random hash function. It just sampled H and Y and it's just sending both of them right away. Okay? There's nothing secret in the verifier's mind. What the prover wants to do, he wants to find a pre-image of Y that maps, a pre-image of Y, but not just any pre-image, a pre-image in the set. Okay? And then, because, the pre-image must be in the set, it's also going to find a proof that certifies that X is, the pre-image is in the set. And it's going to tell the verifier, here, I found a pre-image and I claim it's in the set, here's a proof. The verifier is going to check that indeed it is a pre-image and indeed that the pre-image is in the set. Now, this looks like a priori a bit of a funky protocol, but let's analyze it. We want to argue that the prover will be able to convince the verifier with high probability if the set is large enough, and with small probability if the set is too small. Now, intuitively, let's just understand the extremes for a moment. Let's suppose that S is enormous, is like everything, okay? If S actually equals 0, 1 to the M. Now, the prover will always be able to do this, right? Because everything that is a pre-image is indeed in the set, okay? Now, conversely, imagine the set S is actually empty, okay? Then no matter what the prover does, there's no way he can convince the verifier. So we just checked some, really big extremes. This is just telling you that this protocol is not hopeless. Like, it makes a little bit of sense. Intuitively, as S gets larger, the prover should have an easier time to convince the verifier. As S gets smaller, the prover will have a harder and harder task. Now, this line of choosing the output size in this very particular way is about balancing these two. We want to make sure that the output size is chosen in such a way that in the good case, the prover does have a good probability, and in the bad case, he has a bad probability, and these are kind of bounded away from one another. All right? So that is exactly what we're going to analyze now. Let's first look at soundness. Actually, it's easier of the two. Suppose the set S has size at most b over 2. Now, what we want to study is the probability over h and y, that's the verifier's first and only message, that there exists x in S such that h of x equals y. Notice that this is precisely when the malicious prover can win, because if there is such an x, then the malicious prover can convince the verifier. If there isn't, then he can't. So this is exactly the event we want to study. We want to bound the probability that this happens. All right, we're just going to do a union bound. We're going to say, okay, let's just sum over all possible x's in S and look at, for a particular x, what is the probability that for that x over the choice of h and y, h of x equals y. All right? But look, like y is random, okay? And so there's at most, and for each y, the probability that that x maps to y is 1 over 2 to the L. And we have at most size of S x's. So we can definitely upper bound this event by size of S over 2 to the L, okay? But look, the size of S is at most half of B by assumption, okay? And B, by our choice of L, is at most half of 2 to the L. So overall, this probability is bounded from above by 1/4. Okay? Just pause for a moment so that kind of people are following. Union bound here. Then here, we're just saying that once we have a union bound, the probability that any particular x this holds is at most 1 over 2 to the L, and we have at most size of S x's. We have a bound on size of S because we are in the soundness case. It's at most b over 2. And our choice of b was at most half of 2 to the L. So overall, this is at most probability 1/4. All right. Now, this doesn't tell us anything. We need to make sure that completeness is a probability that is, I don't know, at least a third or a half or something like that, right? So we want some gap between the two. So we need to look at completeness as well. So let's look at completeness. Now, this is actually going to be the slightly harder case, in fact. Now we have that the set is pretty large. It has size at least b, this bound. This is the yes case, okay? Again, we want to study this very same event because the honest prover is going to precisely look at, is there an x in S such that when you apply h to it, you get y. This is exactly like the probability for the honest prover to succeed, right? We just described it here. So we're studying the same event. We want to lower bound this probability. We're going to prove, so we're going to prove this in a moment, that this bound, I can lower bound this probability by 3/4 times b over 2 to the L, okay? This should not be clear why. We're going to just look at that in a moment. Let me just say that because b is at least 1/4 of 2 to the L, then this quantity is at least 3/16, and you have a gap between these two quantities, right? So 3/16 is a constant greater than 1/4, okay? So this would be enough to get a gap between completeness and soundness. Now, I am left to justify to you why this inequality holds. Why do we have this lower bound? All right? Notice that I haven't really used the pairwise independent property yet. Incompleteness is where I'm going to use it. So let's do that. So first and foremost, we're going to assume, without loss of generality, that size of S is actually not just at least b, it's like literally b. Why? Because look, if I make S smaller, like it can only improve, it can only strengthen my point, right? So if S had been larger, this probability grows only, right? So might as well consider the worst case, which is the size of S is exactly b. This is going to help me in my computations, all right? So now we're going to use the inclusion-exclusion principle, okay? This is one of those I don't know, like 4, I don't know, facts about the discrete probability are always used in computer science. There's, union bound, Markov's inequality, inclusion exclusion, Chernoff. Maybe there's like 2 others, but that's it. One of them is inclusion exclusion. So if you're not familiar with it, you should kind of review it. It's a pretty simple statement, but so we're going to use it as follows. We're going to prove that, in fact, for every y, this holds. So we're actually not even going to use, in the completeness case, the fact that y is random. Why? We use the fact that the fact that y is random, we used it already in soundness. Here, we're actually not going to use it. We're only going to use the fact that h is random. So for every y, we're going to lower bound the probability that over the choice of h, that there exists an x such that h of x equals y. We apply inclusion exclusion. What does that say? It says that this probability is at least the sum of the probabilities for x in S, that for that x, if you pick h at random, h of x equals y. But now this is overcounts, right? And exclusion says that because you overcounted here, you need to kind of take away so that you're undercounting again. And so we consider all possible pairs x and x prime in S that are distinct, and we look at the probability that h of x equals y and h of x prime equals y. All right? So this is kind of the collision probability. So this is where we applied inclusion exclusion. All right, but now, so what is this? This is at least size of S times 1 over 2 to the L, okay? Because remember, h is random here, and x and y are fixed. Okay, so we have S of them and 1 over 2 to the L. And this is at most, in fact, exactly equal to minus a half times how many such things we have. We have at most S squared of them, okay? And what is the probability that we have a collision? But that is exactly the pairwise independent condition. So it is 1 over 2 to the 2 times L. All right? So this is exactly we've used the collision probability here. Pairwise independence. Now we just kind of put in our various assumptions. Here, S is equal to B, and B is at most over 2 to the L minus 1, so we can kind of get rid of one S, and we pay for like a plus 1 in the bottom, in the denominator. And then we can actually just rename S by B, okay? And because again, B was at most half of 2 to the L, B over 2 to the L plus 1 is at most a quarter, okay? And 1 minus a quarter is 3/4, and that is exactly 3/4 times B over 2 to the L. So that is the quantity that we had here, okay? This is just some computation that you can just check offline. The only thing that happened is we applied inclusion exclusion. Inclusion exclusion brought in this collision probability, and we understand the collision probability because we are using a pairwise independent hash function, okay? In sum, now we have a one-round public coin protocol that, depending upon whether if the set S is large, then we accept with probability 3/16, and if it is small, like less than half of B, then we accept with probability at most a quarter. These are bounded away from one another, okay? And so this is what we wanted to do. Are there questions here? Yeah.
Yeah, so what exactly are you overcounting in the first step?
This is kind of like the type of Venn diagram that you're putting up. For example, if you have let me see if I can draw it here. So if you have 2 events and you want to look at the probability that you're either here or here, you can't just add up this probability and this probability, right? As a lower bound. That's an upper bound. That's what union bounds do. But if you want a lower bound, you're going to have to subtract the intersection, okay? And that is exactly what we're doing here. We are subtracting the intersection so that we are undercounting again. So inclusion-exclusion basically says if you want the lower bound, you can consider the usual union bound upper bound, but then you have to subtract all the possible intersections between pairwise events, and that gives you a lower bound.
Right.
Yeah, it's just you can also see it with like 3 sets, right? If you sum up all of these things, then you're going to have to subtract all of these intersections, and then you're again undercounting, that's a valid lower bound. And we're looking at the pairwise intersections. Yeah, good question. And anyways, inclusion-exclusion is like, like a basic probability statement that, I encourage everybody to know because it's used fairly often in a sort of a computer science because it's just discrete, again, it's just basic discrete probability. Okay, are there more questions? Yeah.
Yeah, how would you magnify the probability gap? Because if you just repeat it, they would both go to 0.
So the question was, how do you make the gap between these two, which are currently is pretty measly, how do we make it bigger? Well, this has to do with a soundness amplification for interactive proofs, and you can run the protocol multiple times, even in parallel, but then rather than accepting if and only if you accept on all executions, you can accept if you have a majority of acceptances. This is generally how you also amplify BPP algorithms. So, by concentration bounds, if you conduct many protocols, they will be concentrated around, in the good case, in 3/16, right? In the bad case, it will be concentrated at 1/4. So you can just take a majority. And you can prove that if you decide by majority across all the repetitions, then the gap basically grows exponentially fast relative to the number of repetitions. This is something we're not going to look at carefully in this course. If you want to read up on this, you can look at, for example, how you amplify or reduce error bounds for BPP algorithms. It is almost the same thing as this one. When you have two-sided error, you're supposed to apply majority rule rather than all accepts rule. When you have one-sided error, then it's okay to accept if only if other executions accept. Oh wow, so right now we have there's another question, which is currently there's a negative gap. No, it's not fine. I should have chosen constants a little bit differently. Did I really not choose them well enough here? That's pretty embarrassing.
I think it's okay if because 3/4 b over 2 to the L is always greater than 1/2 b over 2 to the L. Right?
Oh yeah. So maybe I applied it in the wrong place. So maybe you're supposed to compare these two. Sorry. Yeah, I'll fix the slides.
I think it can just be 3/8.
Is it 3/8? B is at least... Okay, so I'm not going to try to fix this online. I'll fix it in the slides. Thank you for catching it. There is some sort of magic in the way these things are chosen. I think they're chosen correctly. Maybe I just messed up in sort of showing the gap here. I'm glad somebody's following. That's great. Yeah, you want the soundness gaps to be positive, not negative. And you want them to be at least 1/poly. In this case, it's going to, if you kind of fix this end here, it's going to be some constant. Yeah, thanks for the very good points. More questions or mistakes in this slide? All right, so if not, now we're going to apply the set lower bound protocol to the application at hand. Our application at hand, it was graph non-isomorphism. So let's come back to it. And we want to design a public coin interactive proof for graph non-isomorphism. So that's the theorem we want to prove. I stated it earlier. So here we use the set lower bound protocol for this set that I highlighted earlier. Here I just wanted to point out that the length of a graph, we can just take it to be the adjacency matrix. So it's just 0, 1 to the n squared, right? So the adjacency matrix is a bit at location eij, at location ij, if you have an edge from I to j, for example, okay? So you have like an n squared bit string. Again, this is not literally the set we're going to study. I mean, that it is really there. You're supposed to do the analysis for the other modified set, but again, we're going to still live in this a simplified world where we just have H. Okay, otherwise you also have some other isomorphism there. So the prover and the verifier receive the two graphs as input. The prover wants to convince the verifier that the two graphs are not isomorphic. We're going to set the bound B to be what this set is should be when they're not isomorphic, so it is 2 times parentheses n factorial. The input size of the hash function is n squared in this case. And we set to, this is this choice of L that was in the prior slide. Notice that because B is on the order of n factorial, log of B is on the order of n log n. Now n log n is less than n squared. This is precisely why we needed compressing hash functions, okay? We are in a setting where L is going to be smaller than M, okay? That's why we had to construct compressing pairwise independent hash functions. We're gonna sample what the set lower bound protocol tells us, a random hash function, a random image in the codomain. We send it over to the prover. The prover finds some graph in the set S and an isomorphism that proves that H in the set S. So it's just some isomorphism from H to either G0 or G1, doesn't matter, okay? One of the two. Sends the graph and the isomorphism to the verifier. The verifier checks that the graph is a preimage of the hash function. It checks that H is in the set. How does it check it? Well, it checks that either it's an isomorphism to G0 or to G1. That's enough to check that H is in S. And we already done the analysis. If the graphs are not isomorphic, then this set is large. And we know that the accepting probability for the honest prover is at least something greater than 1/4, ideally. And in the soundness case, because S has size n factorial, then the probability that anybody can make the verifier accept is at most something bounded away from it. Okay, again, just please ignore the constants now because I messed them up in the prior slide. But here we're just directly applying the set lower bound protocol. That is a 1-round public coin interactive proof. And because this set doubles in size in the good case versus the bad case, we can just directly apply it. Okay? Appreciate that this is like a much less, let's call it direct interactive proof, but it's also, not terribly complicated, right? And it demonstrates that here we have a 1-round public coin interactive proof for graph non-isomorphism when maybe in lecture 1 it looked like it was totally essential for the bit to be private unless we're willing to go for something like the sum check protocol. Here there is really no sum check protocol anywhere. Okay? Any questions about applying the set lower bound protocol to graph non-isomorphism?
Yeah, Ale, so it seems like this is a great way to do this for just a generic counting problem. If you want to say, like, you want to, get a proof that some counting problem is bigger than some threshold, right? Does this work in general for that, or is it only, am I missing something?
The question for the others was, this is a great way to basically construct public coin interactive proofs for counting problems. The answer is that, yeah, in fact, the general theorem that I stated at the beginning of lecture that says that every private coin, public coin, so every private coin interactive proof can be turned into public coin interactive proof. The heart of that theorem is precisely to basically distill some counting problem about which you can do a set lower bound protocol. And what is the counting problem that is always there in every public coin interactive proof, in every interactive proof? It is counting the number of random strings that cause the verifier to accept. Because in the completeness case, what happens? The verifier accepts with large enough probability. Well, that means there are many random strings that make the verifier accept. In the soundness case, you know that the probability the verifier accepts, no matter what, is small. That means there is a small number of accepting random strings that the verifier could have used. So basically, in the generic transformation, you're applying the set lower bound protocol over and over to kind of count how many possible random strings are consistent with the transcript so far, and are they large or are they small, okay? And what's messy is just, notation-wise, the fact that you need to do it at every round. So it's just like notationally heavy, but that is exactly kind of what is happening in the full general case. You're counting how many random strings are there that lead the verifier to accept. If you're interested, I encourage everybody to look up this theorem, because it's the fact that it holds at such generality is pretty impressive. Now, all of p-space includes counting problems like p to the sharp p, so in particular that gives you such a thing. Now, whether you can directly apply this technique to specific counting problems, I haven't loaded state about that. It is possible. Remember though that you need some gap, right? So here we have a gap between 2n factorial and n factorial. Also, in the general case of public coin interactive proofs, you have a gap. So in the general case of any interactive proof, you have a gap from 2/3 to 1/3, right? So whatever counting problem you're studying, you need to make sure that you have some gap, right, that you can exploit. And then probably you can apply the set lower bound protocol. Good question. Now, there was another question here, if I can review why we need specifically a compressing hash function. So let me explain that. Now, the input size here that we have is n squared. That is an adjacency matrix describing the graph. So it's n squared bits in a matrix n by n, where location ij tells you whether there's an edge from I to j. The set lower bound protocol tells us that we should pick the output size of the hash function to be on the order of log of the size of the set. Now, the size of the set is n factorial. Now, log of n factorial is order of n log n. Okay, why? Because n factorial is roughly n to the n, it's really n over e to the n, right? So it is order of n log n when you take log of that. So the output size is n log n, the input size is n squared, and so you see that the output size is smaller than the input size. That's why we needed a compressing hash function. Good question. Are there more questions before I'm going to move on? I don't see more questions, so I'm going to move on. So the last part of this lecture, we're going to look at something that maybe some of you are bothered by it. Notice that we started from a problem for which we had a one-round private coin interactive proof with perfect completeness. The honest prover always is able to make the verifier accept in the good case. But now, in the good case, the prover only has like a high enough bounded away from soundness to convince the verifier. Sometimes it just fails. That's kind of annoying. So one may ask, okay, well, private coins were not essential, but what about public coins? Maybe when you want to start transform protocols into public coin ones, maybe you lose something pretty, I wouldn't say important, but like nice, which is perfect completeness. So again, now we're going to see some some sense also amazing fact that this is actually not essential. There is like a generic transformation that says that if you have a language that has a k-round public coin interactive proof, for example, 1 round for GNI in the prior slide, then L also has a k+1 round, so 1 extra round, public coin interactive proof with perfect completeness. Okay, so at the cost of 1 extra round, you can just recover perfect completeness right away. All right? It is always true, and in particular, it is true for GNI. And in that case, it would give us a 2-round public coin interactive proof for GNI with perfect completeness. As I wrote here. So the ideas behind this theorem are very closely related to a complexity fact that you may have come across if you are versed in complexity. That is Clemens-Lautemann's proof that the complexity class BPP is in the second level of a complexity hierarchy. BPP are probabilistic polynomial time, are languages decidable by probabilistic polynomial time algorithms with two-sided error, okay? And the second level of polynomial hierarchy, in this case sigma 2, is I think that exists for all, okay? So it exists for all, that some Boolean formula is true. Now, because they're closely related, I'm just gonna quickly go through, like in half a slide, this proof. It might come off as not entirely, I mean, a little bit fast, but mostly I'm going to go through it again slowly in our case. I just want to put it down first for those that are already familiar with it, and also for those of you who are not familiar with it, then I can later come back to the slides and appreciate how the case of interactive proofs is very related to the case not about interactive proofs, it's about just algorithms, okay? And historically, that's indeed where it came from. So this result was really proved because we had a good understanding of this type of results. Now, so here it is. So we want to prove, hey, we're going to do it, pretty cursor in a very short way. We want to prove that some languages in BPP is in fact in sigma 2 to the p. So suppose some language L is decidable by a probabilistic polynomial time algorithm M, okay, with error bound epsilon. It means that in the X case, the algorithm M, so in the yes case, the algorithm M says yes with probability at least 1 minus epsilon, and in the no case, the probability that the algorithm says yes, that's a mistake, is at most epsilon, okay? So the error on both sides is bounded by epsilon, all right? Now, by repetition and majority, this is exactly the question I was asked earlier. How do you amplify this? We can actually assume that the error that we have in two sides is strictly less than some quantity, 1 over m, where m is the number of random bits used by the algorithm, okay? So somehow this 1 over m is going to become important in a moment. But simply because I can exponentially fast reduce the soundness error, I can ensure that this soundness error, this kind of two-sided error, is strictly less than 1 over the number of bits that my algorithm is using. Now, given instance x, we can define a of x, standing for accepting. A of x are all random strings for which this algorithm says yes. Now, if x is in L, then I know that the number of such random strings is at least 1 minus epsilon times 2 to the m. That's like the number of accepting random strings. That's what the error bound epsilon tells me. If x is not in L, then I don't have too many random strings that make me accept. There is at most epsilon times 2 to the m. Now, we will not see the derivation, we'll see it in interactive proof case, but roughly speaking, there is a way to use the probabilistic method to show that in the yes case, I can basically smoothen out this large set by a small number of shifts to cover everything. So I can take m shifts such that no matter which random string I pick, there is a shift that puts me inside the set. All right? Because this set is so large, it's at least 1 minus epsilon times 2 to the m, right? It's almost everything. I can pick m shifts of it such that no matter where I find myself, there is a shift that covers me. Okay? Now, conversely, by a union bound, when the set is small, no matter which shifts I consider, there is always some string that is left uncovered by all shifts. Okay, this is some kind of intuitive, right? So we have this set of accepting things. If it's too small, a small number of shifts is not going to cover everything. But if it's big enough, a small number of shifts is going to cover everything. Now, why would we ever consider these two conditions? Because those are exactly the conditions for the completeness and soundness in the second level of polynomial hierarchy. It says, is it the case that you have a witness y such that for all z, the formula phi of x, y, z equals 1? And is it the case that for all y, there exists z that falsifies the formula? Okay? This is exactly what is required for L to be in a sigma 2 in the polynomial hierarchy. Now notice from what we are interested in is that the completeness case has suddenly no error. The error disappeared. Why? Because kind of whatever error there was here, we are taking care of it with some shift. So there's no more error here. This two-sided error now just really went away. All right? So intuitively, this idea that if we have a large accepting set, we can just kind of smoothen it out with a small number of shifts and make the error go away is exactly what we're going to use to prove this theorem. Okay? But here I skipped many steps. What do you mean a probabilistic method? What do you mean the union bound? Well, there's a computation for that, and we're going to do it just for our case. But the very same computations are happening in this proof. Okay?
Hi, Alejandro.
Yeah.
Is such a shift computable in polynomial time?
The question was, can the shifts be found in polynomial time? Actually, most shifts work. Now, that doesn't really help because we'll introduce more error. If you want to have an actual shift, you may have to work hard. In general, both the transformation that we saw earlier and this transformation as well do not preserve efficient provers. So for now, we're again in this regime where we're just trying to understand what can interactive proofs do in a very general sense, if all we really are interested in is a polynomial time verifier. Right now, if they exist, the honest prover can find them because they exist. Most of them are good, what that's the computation says, but still, how do you check that it's good? That may be like an expensive computation. And if you just pick it at random and hope for the best, you again have a soundness error. A completeness error. So no, finding them is not efficient in general case. Good question. More questions? So this was just like a kind of some primer, and you don't need to necessarily be familiar with this complexity class sigma 2. It's just whatever this class is, it doesn't have an error in the completeness case now. Okay, because we've smoothened out via shifts like the large enough probability of accepting. All right, so now let's prove this theorem, and we're just basically going to retrace these things slightly more complicated for our case. So, all right, let's start slow again. So this is the theorem we want to prove. We have a k round public coin interactive proof. We want to construct a k+1 round public coin interactive proof, but now we want there to be no error in the completeness case. We want to have perfect completeness. All right, so give me the k round public coin interactive proof for L. So here it is. Let m be the number of random bits used by the verifier. Before it was the number of random bits used by the algorithm. Now it's the number of random bits used by the verifier. Okay? And we assume that the completeness and soundness errors are bounded from above by, before it was 1 over m, now it's going to be 1 over 3 times 1 over m. And just like before, this is without loss of generality because we can parallel repeat and rule by majority, and this is going to exponentially fast reduce the soundness error. So this is something that is okay to assume. Now we're going to define a set related to the previous one, kind of like accepting randomnesses, right? So now the set doesn't depend just on x, it depends also on the prover, right? Because with some particular choice of randomness and a particular choice of prover, I may or may not accept. It depends what the prover says, right? Previously, in the case of BPP, there were no provers, so it didn't figure in the definition. So now we're going to say, for a particular prover in a particular instance, let's consider all random strings that lead me to accept. And like before, if X is an L, then this is a large set where the prover that I'm considering is the honest prover. And in the no case, regardless of which prover I consider, this is a small set. Okay? So what is going to be similar to the Lautmann's proof is that we're going to use this exists for all or for all exists characterization of X in L and X not in L, okay, for these two cases. And the difference is that kind of this randomness shifts must account for multiple rounds, right? It's kind of this, we're kind of shifting and smoothing things, but in the meantime, the prover is running. So what do you mean you're shifting the randomness, okay? So we need to look at that a little bit more carefully. So let's look at that more carefully. So we're gonna now explicitly write down the new interactive proof for L, okay? It's gonna have k plus 1 rounds, and we're gonna argue it has perfect completeness. So let's denote it P star and V star. Again, the verifier has this randomness R, okay? It consists of m bits. Now notice that because we have k rounds, we can chop up this m bits into blocks. The block R1 for the first round, the block R2 for the second round, and so on and so forth, right? Because we're in a public coin protocol, if we have k rounds and a total of m bits, we have these k blocks of randomness that are kind of scattered through the k rounds. Now, the first instructions for the honest prover are to say, please find m shifts such that regardless of what, like the prover doesn't know what randomness the verifier has in his mind. But here it's going to say, doesn't matter. There is going to be a shift that puts this shift an accepting randomness for when I play the honest prover. Okay? This is the honest prover of the interactive proof we're starting from. Now, can he do it? Well, we need to argue that. But let's say he can do it. All right? He's going to send these shifts to the verifier. And now they're going to simulate k rounds of the previous interactive proof, but not just k rounds. It's going to simulate m parallel executions of that interactive proof at once. This is not the parallel executions that let us reduce the soundness error. That's like, we already forgot about that. This is a different parallel execution. So we're going to run them in parallel. So we have k rounds, and in parallel we're going to run these m executions of the already amplified interactive proof. So how do they look? Well, in each round, the prover is going to say m messages, one for the first execution, one for the second execution, and we are around j, so that's why we have the index j here. And the verifier is going to provide one randomness rj, and how is the prover supposed to play? Well, he's going to take this randomness rj and he's going to play the ith execution by shifting the randomness by the ith shift. So he's going to say, okay, I'm the prover. I received randomness rj, but I am playing in the ith slot as if the randomness had been shifted by si. Now, both r and s can be divided in blocks for each round. So here, for example, I run the honest strategy as if in the first round I received the XOR of the R1 and the first part of SI, right? And so on and so forth, up until, whatever I received so far, and that's my next message, right? So I'm playing the shifted execution. So now the honest verifier is basically playing this m simultaneous games with the prover. He's going to accept if any one of them is good. He's going to say, look, I have played m executions, m shifted executions. If any of the shifts accepts, I'm going to accept. Intuitively, this is the smoothing, right? We wanted to say that if there is any of the shifts that leads to a good outcome, I'm happy to accept. Okay? Because we want to help the honest prover always pass, right? Is the description of the protocol clear? we are running m parallel executions of the underlying public kernel interactive proof. Each of the executions is shifted by one of the m shifts, and these shifts are chosen in such a way that regardless of what randomness the verifier has in his mind, there is a shift that will make us accept. Okay? All right, let's analyze completeness.
Is it also important here that the number of shifts be not too much? Otherwise, a malicious prover can always break down.
Sorry, I didn't understand the question. Is it important that what is not too much?
A number of shifts, so the M.
Yeah, so it's important that this number of shifts is not too much. We want it to be basically just good enough for covering everything. But then if it's too many, then in the bad case, we're going to have a problem, right? So you're balancing these two things.
Right. Okay.
So you want kind of enough of them to cover everything, but then you kind of reduce your soundness error enough so that if you consider all m shifts, then there's always one randomness that kind of voids it. In this case, we don't just need one, like in the case of BPP, we need several randomnesses because we want the soundness error to be kind of still pretty good, right? Good question. So suppose X is an L. Now I want to argue that the honest prover is always able to make the verifier accept. So first we should realize that if indeed the honest prover is able to do this, then we're fine, right? Because if he does find these M shifts such that regardless of what randomness is used, there is some shift that causes the verifier to accept on that randomness, then that shift is going to be somewhere here and we're covered. So we just need to argue that in the completeness case, there is a good set of shifts to find. To argue that there exists such a setting of shifts, we use the probabilistic method. We're going to prove that they exist with probability greater than 1. Sorry, greater than 0. Equivalently, we're going to prove that the probability that they're bad is strictly less than 1. Okay? So we look at the probability that for random independent choices of shifts, the probability that they are bad, namely that exist are such that all shifts are not in the accepting set, is less than 1. That's what we want to show. Well, we can do a union bound, so we sum up over all r's, and now we just consider the probability that for that r, m random shifts are such that all of them are bad. Okay? Now, how many r's do we have? We have 2 to the m, okay? And notice that now, because all these s's are random, it doesn't matter what is r, right? The fact that we're shifting by r, we can just forget about it, okay? It's all equal to this event, because these are independent, okay? So just a uniform random string, the fact that I'm shifting them by something doesn't matter. Okay, but those are independent events, so each of them, the probability that they're there, it is at most the size of that set, so it is epsilon. And we have m such things, we're asking all of them are outside, so it is epsilon to the m. Okay, well, epsilon we assumed was at most 1 over 3 to the m, 1 over 3 times m, and this entire thing is strictly less than 1. It's not just even strictly less than 1, it's like much less than 1. So it's saying that most choices of S are good. All right, so again, we've shown that over a random choice of S, the probability that they're bad is less than 1. So there must exist a good choice of S. So the honest prover is covered here. All right, so we're only left to look at soundness. So suppose that X is not in L. So we want to argue that soundness error is at most a third. That is going to be enough, right? Because we already argued that we have perfect completeness. A third is definitely less than 1. And now the soundness gap is positive rather than negative. Now, for this, it suffices to show that for a fixed kind of I, the probability that a malicious prover wins specifically in the ith execution is at most epsilon, which is, we assumed, was 1 over 3 times 1 over m, right? Because whenever the prover wins, he has won in one of the executions, either the first one or the second one. There's only m executions. So if for any execution, the probability you win that execution is at most a third times 1 over m, then the probability you win in any execution by union bound is at most 1 over 3, right? So now we can just focus on the ith execution and prove that the probability it wins in that one is, reasonably small. All right, so fix an arbitrary malicious prover. That prover is going to say something in the first round. So these are the shifts he chose. And we're going to define the randomnesses that cause the prover to to win in the ith execution, right? So what does it mean? It says we pick a random string from the verifier. We ask what the prover would have said in the first round and look at the ith slot in his answer, right? This is his move for the ith execution, right? Because he outputs an answer for all m executions, but right now I'm just interested in what he says for the ith execution. And in the ith execution, the verifier is reasoning relative to this shift, r specifically shifted by si. Now, we want to claim that this set has size at most epsilon, okay? And that will be done, right? Because if that's the case, then that's the probability he wins in the ith execution. So suppose by contradiction that it's not. Suppose it's greater than epsilon. We're going to construct a prover that is tailored to the ith execution that wins in the original interactive proof. Okay? With probability greater than epsilon, which is a contradiction, right? Because the original interactive proof we started from had error bounds at most epsilon. So no prover can win with probability greater than epsilon. Intuitively, this should make sense, right? We have a prover that is pretty successful in the ith execution, so we can just pull out from it something that just wins in the original proof, right? Because the ith execution is it's just a shifted version of the original one. So we're just going to de-shift things and making play like that, right? So the new prover we construct is going to run p tilde to get these shifts, and is going to just remember the ith shift. Remember, these shifts are not exposed to the other verifier because he doesn't know about those shifts from the original interactive proof. In the jth round, he has received verifier messages b1 through bj-1, and pi tilde is going to compute its next message as follows. It's going to say, okay, these are the messages I received. Let me see what this very capable prover to win in the ith execution did say if I ran him on the ith shift, because he lives in that world, so I have to create that world for him, right? And I'm gonna just pull out what he said in the ith execution, right? That is how I compute my next message. And now I want to argue that for any randomness that was in this set, I have a corresponding randomness where this prover wins, okay? And so that shows that this prover wins in the original interaction, the original interactive proof with probability that is greater than epsilon, okay? But that's easy, right? So I have a random string where this new prover wins in the ith execution. This is exactly what it means to do that. But if I open up what this means, that means that this prover, by construction, is winning when I pass him these things as input, right? Because then if I pass this as input, here, the two shifts cancel out, right? And we're having p tilde running on Ri, okay? But this is exactly the condition for this being an accepting string for pi tilde in the original interaction. So this says that these two sets are the same. This is the end of the soundness proof. This is the main difference between this and Lautemann's proof that BPP is in sigma 2 is just that we can't just shift. Once we have a prover and we have to shift him at every round, okay? And to argue that the prover winning in the ith execution with noticeable probability means that he could have won by himself in just the original interactive proof if I just unshift things for him, okay? And this proves that once I handshifted that guy, he is a pretty good prover for the original interactive proof, which is a contradiction. So he could not have won the ith execution with high probability. And this tells me that winning any of the executions has probability at most 1/3. Okay? Are there questions about this? I think it is a pretty remarkable proof. There is some, again, more techniques that don't have to do with arithmetization. Curiously, many techniques that don't have to do with arithmetization are inefficient for the honest prover. We'll pretty soon come back to honest provers very explicitly to make them efficient. But it's pretty amazing, right? So you want to, at a very high level, what's happening is that if you want to recover perfect completeness, you use these shifts to kind of give the opportunity to an honest prover to find one execution where he can win. And if you pick enough shifts and your soundness error is small enough, then there is always a shift that makes the verifier accept with probability 1 in the good case. And in the bad case, because the soundness error is small enough, you don't have too many shifts, then there is always like a noticeable fraction of the randomnesses that make the verifier reject. Yeah, this is kind of what's happening here. The shift idea was born kind of in sort of in a world that wasn't about a perfect completeness. It was about putting BPP in the polynomial hierarchy, but because the polynomial hierarchy doesn't have a notion of soundness error, then somehow this soundness error had to be overcome, and it was done through the shifts, and these shifts could have well repurposed later to show perfect completeness.